Okay, this is H10J.3 Property of Curves summary sheet. I pretty much made this from chapter 19 of the Hayes Math Applications SL book. It does a really nice job of talking about the different vocabulary that we need for this chapter. So first of all, a stationary point is when the derivative is equal to 0. So when the derivative is equal to 0, that means it's tangent to the horizontal. So that happens either, if you can see this picture, you can see here's my function, and the derivative is equal to 0 at these two points here, at -2 and at -4. So that's a stationary point, and we usually get a local maximum or a local minimum. Okay, so this one here is a local maximum. This is a local minimum. Okay. Um, a global minimum is any point that is truly the lowest point. This is the global minimum. A global maximum is this point here, where it's truly the highest point. So there's your global maximum is right here. This is your global minimum. It's right there. Okay. Um, and as we said here, the local maximum is this guy right there, and the local minimum is this guy right there. Okay. Okay. Now we're going to talk about stationary inflection points. So when the first derivative is 0, we either have a local maximum or a local minimum. Usually. Usually. Because in some examples, that's not true, like it says here. So if I've got y equals x cubed, I could just put that into a calculator. X cubed, and we graph that, and it looks like what you see here on this picture. So the first derivative is 0 here, but we don't have a maximum or a minimum. What we have is we have a stationary inflection point. Okay, it's right here, stationary inflection point, or it's just an inflection. Okay, and we'll be talking more on this. So this tangent is horizontal, but at 0, 0, but it's neither a maximum or a minimum. But it does have a horizontal tangent. Okay. Okay. So now I'm going to talk about sign diagrams. So here is a sign diagram of the first derivative. Okay. So if we look here at this picture here, okay, all of these places, anywhere between this dot and over here, you can see the slope is going up. That means I have a positive slope, and that means the first derivative is going to be positive. Between this dot here and this dot here, the slope is going down, isn't it? So whenever the slope is going down, we have the first derivative is going to be negative because it's going down. When the slope is down, the first derivative is down. And then between this point here and this point here, we have a positive slope. And so in this positive slope, we have a positive first derivative. And same thing here. The slope is positive, so that means we have a positive first derivative here. Okay. So this is my sign diagram. Okay, and this is the sign diagram for the first derivative. We'll be talking about second derivative sign diagrams in just a minute. Okay, so whenever it's kind of pointing down like this, from a the slope here is originally positive, and then the slope is next negative. So if my sign diagram for the first derivative goes from positive to negative, then we're going to have a local maximum. Okay, so the first derivative goes from positive to negative, and then we have the first derivative is 0. At that point, we know we have a local maximum. Okay. If we ever have a minimum, local minimums always happen when we go from a negative slope then to a positive slope. And right at point A we have a horizontal slope where the first derivative is 0. Okay, so that's just like it says right here. The first derivative is 0 at these points. And it goes from a positive slope to a negative slope, we get this. If it goes from a negative slope to a positive slope, we get this. Okay, and then we have our inflection points. Here's two examples of inflection points where the slope is positive here and positive here. So so here, once again, we have the first derivative is 0, but we've got, I'll just use orange. Okay, we've got positive and positive, or we've got negative and negative. Okay, negative slope on this side and negative slope on this side, and the derivative is 0. And those are all the possible combinations. Positive to negative, negative to positive, positive to positive, negative to negative. Okay? And then here's an example. And you can figure out whether a point is a minimum or a maximum based on the sign diagram. So if I take the first derivative of this, we get this, and then I can factor this out. And we know that when x equals 3 and when x equals -1, in this example, we're going to have a minimum or a maximum or a stationary point. So that when I'm making my sign diagram, I draw a line, and then I have a mark here at -1, and I have a mark here at 3. Okay, and then I can plug in a value into here, and then I figure out. So let's plug in a number smaller than -1. Like if I plug in -2 into my derivative formula, we would end up with a positive value. If I plug in a number between -1 and 3, like how about 0? If I plug in 0 in here, I have 3 times 0 minus 3 and 0 plus 1. 3 times a negative times a positive is going to give me a negative. So you can plug in a random number. I could plug in 4. Right? If I plug in 4, I end up with 3 times 4 minus 3, which is positive, and 4 plus 1, which is positive. So positive times positive times positive is going to give me positive. And so we can go back here whenever I go from a positive slope to a negative slope, we know this one's going to be a maximum. We're going to have a maximum at -1. And then if I go from a negative slope to a positive slope, we have a minimum. Okay? So local maximum. Okay. Now, the next part, we're going to be using the second derivative to help us talk about the shape. Okay, so the second derivative helps us deal with the shape. So we're or the curvature. So if it looks like this, this is called concave down. Okay. I'm going to highlight that blue because it looks like a sad face. Boo hoo hoo. Okay. And this is concave up. And I think of that as a happy face. Yay! Okay. So there's my happy face and there's my sad face. Now what makes it happy and what makes it sad, other than my imagination? Um, so if we look here at the slope, at this point we've got a slope of 2, then we have a slope of 1, and the slope becomes 0, then the slope becomes -1, and the slope becomes -2, and so on. The slope gets steeper and steeper here. So whenever the curve increases in steepness, then we've got concave down. So here, like over here, it's not drawn here, but let's say we have a slope of 3, then a slope of 2, then a slope of 1, then a slope of 0, slope of -1, slope of -2, slope of -3. So as the first derivative gets smaller and smaller and smaller, 3, 2, 1, 0, -1, -2. As the first derivative decreases, then we know our second derivative is going to be less than 0. Whenever the second derivative is less than 0, we've got concave down. That's concave down. Or if the second derivative is negative. Okay, so if the second derivative is negative, we have concave down. Likewise, if our second derivative is positive, then we're going to have concave up. When the second derivative is positive, we have concave up. Okay. See, we go from a slope of -2, -1, 0, 1, 2. My slope is increasing. Okay. So, and basically that's what this says here. So concave up looks like this. Concave down looks like this. Okay. Okay, find the intervals that are concave up and concave down. So if I take my first derivative, we get this. If I take the second derivative, I get this. So in order to make this equal to 0, if I have 2x minus 1 equals 0, I can add 1 on both sides. I get 2x equals 1. Divide by 2, I get x equals 1/2. So we know when x equals 1/2, the second derivative is equal to 0. Okay, and so when the second derivative is 0, at that point, so values less than 1/2, we have negative, and values greater than 1/2, we have positive. So if we've got the second derivative is negative, this is going to be concave down, and here values greater than 1/2, we have concave up. Okay, so concave up for values greater than 1/2, and concave down for values less than 1/2. Okay. If you go back and look how I highlighted on the first page, or even the second page, I guess, I did the same thing. Well, we'll go back to that in a second. Okay. Um, so here I took the first derivative using the quotient rule, and and then I took the second derivative, and we get this. So in order to make um, uh, this equal to 0, so to make the second derivative equal to 0, we know that x minus 3 equals 0. And if I add 3 on both sides, we have x equals 3. Okay, so something happens here at 3. But if I look at my original function, we know that x is not equal to 3 because I would have 0 in the denominator. So we're going to have an asymptote at 3. So let's just put that in the calculator so we know what that looks like. So if I have um, parentheses x plus 1 close parentheses divided by parentheses x minus 3 close parentheses, and if I graph that, we get a graph like this. So we have a vertical asymptote at 3. I'm just drawing a sketch just so you can see. So it looks like this. So we've got a vertical asymptote at x equals 3. Okay. So to the left, that looks like half of a sad face, doesn't it? And so hence we've got a negative sign. We have concave down for values less than 3. Greater than 3, we're going to have positive values in here. So like 4, 4 minus 3. We have positive values here in our second derivative. And if you look at our graph, notice this looks like part of a happy face, doesn't it? Okay. So now we're putting it all together. Okay, an inflection point. When we have inflection points, um, that's when the graph switches from concave up to concave down. So at inflection points, the second derivative equals 0. So here I go from concave down to concave up. Okay. So here's two examples where our inflection point, we have a stationary inflection point, a non-stationary inflection point. But an inflection point is when it goes from, when it switches concavity. Okay, these are concave down, and on the other side, it's concave up. So second derivative, when the second derivative is positive, we get concave up. When the second derivative is negative, we get concave down. And at the stationary inflection point, it's when it switches from one concave to the other. Okay, so when I'm looking at the second derivative, at the stationary inflection point is when the second derivative equals to 0. When the second derivative equals 0. Double prime equals 0. Okay. Okay. So once again, this is the second derivative. And when that's equal to 0, it goes from concave down to concave up. Okay. Now over here, it's still going down, right? It's down, negative here and negative here. So in this example, negative and negative, And it also happens in example when it's positive and positive. Oh, sorry. All these different things happening when the signs of the first derivative change and then when the signs of the second derivative change. So on both sides here of this non-stationary inflection point, it's negative on the left and it's negative on the right, and still negative at the inflection point. See, if A is right here, it's negative on one side and negative on the other. It's going down. Okay. All these different things. So here is a summary. So turning points happen when the first derivative is 0, and we get a maximum or a minimum. Okay. Stationary inflection points, you can see that it's concave up here and concave down. And we have non-stationary inflection points, which also switches from concave down to concave up, or concave up to concave down. And this all of these different things are affected by first derivative and second derivative. Is that it? That's it. I hope this helps you with the other handout in conjunction.